Module 7, Lecture B, Greedy in Python. By the end of this lecture, you will be able to use Python sorting and heapq to implement efficient greedy selections, translate high-level greedy strategies into clear, maintainable Python code, and measure and interpret the performance of greedy implementations on realistic input sizes. Sorting for greedy, custom key sorting. In greedy algorithms, sorting is not just about using the default order, but about ranking items by a specific priority, such as earliest deadline or highest value per cost. Custom key sorting lets us map each item to a priority value, and the sort uses these values to decide the order. This is essential for making sure the algorithm picks items in the right sequence. For example, when scheduling meetings by their finishing times. By encoding priorities as keys, we keep the selection rules clear and easy to adjust when the problem requirements change. Custom key sorting lets you define complex priority rules by combining several attributes and transformations into a single sorting criterion. For example, in scheduling, you might sort tasks first by deadline and then by processing time or penalty. And in resource allocation, you might sort by value to weight ratio and break ties with another attribute. By changing only the key, you can switch between different greedy rules without altering the underlying sorting procedure. This makes it a flexible and efficient way to manage priorities in many optimization problems. When using custom key sorting in large greedy algorithms, it is important to design the key function carefully. The key assigns a priority value to each element so the algorithm can order them efficiently. A simple, clear key keeps the computation fast, even for very large datasets, and makes it easier to test and adjust. By balancing how expressive the key is with how efficient it remains, you can maintain both correct greedy behavior and good performance. Python code, custom key sorting. This section focuses on using custom key functions to control how tasks are sorted in a greedy selection strategy. You should demonstrate how to sort tasks first by their earliest deadline and then, when deadlines are equal, by their shortest duration. Clearly contrast this custom priority-based sorting with the default sorting behavior so the effect of the key functions is easy to see. Standard libraries are enough for this demonstration, so no additional installation is required. We represent our tasks as a list of dictionaries, where each task has a name, a deadline in days, and a duration in hours. This structure makes it easy to manage the tasks and sort them based on these attributes. In our example, we have 4 tasks labeled A through D, each with its own deadline and duration. Using this setup, we can demonstrate sorting techniques that prioritize tasks according to their deadlines and, if needed, their durations. We begin by printing a message to show that we are about to display the tasks in their original order, which establishes the initial state before any sorting happens. Then we go through each task in the list and print its details. This lets us see the current sequence of tasks, along with key attributes like name, deadline in days, and duration in hours. Having this clear starting point makes it easier to compare and understand the effects once we apply sorting later. The greedy priority function defines how tasks are sorted for scheduling. It takes a single task, represented as a dictionary of task details, and returns a pair, made of the number of days until the deadline and the hours needed to complete it. This pair is used as the sorting key, so tasks are ordered first by how soon they are due, and then by how long they take. As a result, tasks with earlier deadlines and shorter durations are prioritized, which follows a greedy strategy for managing tasks. We sort the list of tasks using a custom priority function as the sorting key. This function ranks tasks first by how soon their deadline arrives, measured in days, and then, if deadlines are the same, by how short their duration is, measured in hours. The result is a new list where tasks with earlier deadlines come first, and ties are broken by choosing the shorter tasks. This ordering helps us select and schedule tasks efficiently based on these two criteria. We begin by printing a message that explains the tasks will be shown in order of their deadlines and, when deadlines match, by their durations. Then we go through the sorted list of tasks and print each one's details. This lets us visually check that the tasks are correctly ordered first by deadline and then, if needed, by duration. Overall, this makes it clear how the custom sorting logic has been applied. This script shows how to use a greedy strategy to sort tasks with custom priorities. Each task has a name, a deadline in days, and a duration in hours. The tasks are reordered using a custom sorting rule that first selects the earliest deadline and, when deadlines match, chooses the shorter duration. After sorting, the tasks are printed again in this new order. This demonstrates how custom sorting can help optimize which tasks to do first and illustrates the flexibility of Python sorting tools. Choosing sorted or sort. When using sorting in greedy algorithms in Python, you can either create a new sorted sequence or sort an existing list in place. Both give you the same order, but creating a new sequence keeps the original list unchanged, which is helpful if you want to compare different strategies or debug your decisions. This lets you, for example, sort the same data by different criteria while still having access to the original version. Sorting in place is better when you do not need the original order and want to save memory and improve performance. When you have a list where the original order does not matter, sorting it in place is often the most efficient choice. This means you reorder the existing list instead of creating a new one, which saves both memory and time. It is especially useful in greedy algorithms, such as when you sort tasks by deadline before making decisions. This approach is also important in performance-sensitive situations like processing large event logs or scheduling many tasks, where avoiding extra data structures helps keep your program fast and memory efficient. When designing a greedy algorithm, your choice between creating a new sorted sequence or sorting data in place affects both clarity and structure. Building a new sorted sequence works well with expression-based code and pipelines, making the flow from raw to sorted data easy to read. Sorting in place instead emphasizes a step-by-step transformation, which can feel natural when the algorithm moves through clear stages. Being deliberate about this choice helps keep greedy algorithms efficient, readable, and maintainable as your codebase grows. Python code. Choosing, sorted, or sort. demonstrate how to choose between using a function that returns a new sorted list and one that sorts a list in place when making greedy style selections. Emphasize the difference between preserving the original list and modifying it directly. Finally, print and compare the results so the different behaviors are clear and easy to see. The script explains that you do not need to run any pip install commands because it only relies on Python's standard library. All the required functionality is already built into Python. As a result, you can run the script without installing extra packages. This makes setup simpler and ensures the script is easy to use. We create a list of job offers, where each job is stored as a dictionary containing its title, salary, and commute time in minutes. This structure lets us keep all job information organized in one place. Because each job has the same set of attributes, we can easily compare them by salary, commute time, or other criteria. It also makes it straightforward to perform operations like sorting or filtering based on these attributes. We create a new list of jobs, ordered from the highest salary to the lowest by using a sorting function on the original list. This function uses a small helper, called a key function, to pull out the salary value from each job entry. By telling the sort to work in reverse, we make sure the jobs with higher salaries appear first in the resulting list. We use a sorting function to create a new list of jobs ordered by the shortest commute time. A key parameter uses a small helper function that pulls out the commute minutes from each job's data. This makes sure the jobs are sorted by commute duration. The original list is not changed, so we can view the jobs in this new order without altering the initial data. We display a message to confirm that the original list of jobs remains unchanged after using the sorted function, showing that this function creates a new list instead of modifying the existing one. To present the results clearly, we then use a list comprehension to pull out only the job titles from the original list. This keeps the output focused and easy to read or interpret. This line of code prints the job titles from a list of jobs that has already been sorted by salary from highest to lowest. It uses a list comprehension to pull out only the title field from each job entry. This highlights a greedy strategy where the jobs with the highest salaries are selected and shown to the user first. This line produces a view of the jobs ordered by the shortest commute time. It uses a list comprehension to pull out just the job titles from a list of jobs that was already sorted with the sorted function. This reflects a greedy strategy that favors jobs with the shortest commute. It also shows how sorting can give different perspectives on the same data without changing the original list. Here we sort the list of jobs directly, changing the original list rather than creating a new one. We call the sort method on the jobs list and use a key function that pulls out each job's salary so the list is ordered by that value. By setting the reverse option to true, the jobs are arranged from highest to lowest salary. This method is appropriate when we do not need to keep the original order, because it permanently rearranges the elements in the list. The code first sorts the list of jobs in place by salary, so the original list is now permanently ordered from lower to higher pay. It then goes through this sorted list and prints each job title in the new order. This makes it easy to scan the jobs by salary, especially if you want to focus on the higher paying positions. This script compares using the sorted function with using the sort method in Python. It starts with a list of job offers and uses the sorted function to create new lists ordered by highest salary and by shortest commute, leaving the original list unchanged. This shows how sorted returns new lists without modifying the original data. The script then prints job titles in each order to illustrate different greedy choices. Finally, it uses the sort method to reorder the original list by salary in place, demonstrating that sort permanently changes the list when you no longer need its original order. Stable sort behavior. In greedy algorithms that depend on sorting, it's important to know that Python uses stable sorting, which means items with equal sort keys keep their original order. This stability lets you rely on a main sorting criterion, such as deadlines or profit ratios, while automatically preserving a consistent tie-breaking rule. For example, if two tasks share the same deadline, the one that appeared first in the input will still come first after sorting. This predictable behavior helps maintain both the correctness and efficiency of the greedy strategy. Stable sorting is especially useful when a greedy algorithm needs to sort the same data multiple times using different criteria. You can first sort by a secondary factor and then by a primary one, and any ties in the primary sort will keep the order from the secondary sort. For example, if you sort jobs by processing time and then by deadline, jobs with the same deadline will still be ordered by processing time. This lets a greedy rule, such as choosing the earliest deadline and breaking ties with the shortest job, work correctly and consistently without extra tie-breaking logic. Stable sorting is important in real-world applications because it preserves existing order while allowing efficient, greedy choices. For example, in a clinic, you can sort patients by urgency, but still keep their original check-in order. And in finance, you can sort transactions by risk while keeping them in chronological order when scores match. By maintaining this context, stable sorts help greedy algorithms remain efficient, predictable, and fair over time. Python code. Stable sort behavior. This example uses simple job scheduling to demonstrate stable sorting. When jobs are sorted by a primary key, such as priority, stable sorting ensures that jobs with the same priority keep their original relative order. The example also illustrates a two-pass sorting process, where a second sort is applied on another key but preserves the ordering created by the first sort. Together, these ideas show how stable sorting maintains consistent and predictable job order even when multiple sorting passes are used. The script explains that you do not need to run any pip install commands because it only relies on Python's standard library. This means all the required features come from modules that are already built into Python. As a result, you can run the script without installing extra packages. This keeps setup simple and makes the script easier to use. We represent each job as a dictionary that stores its name, deadline, and processing time, and then place these dictionaries into a list. This structure makes it easy to manage the jobs and sort them based on any of these attributes. In our example, the list contains 4 jobs labeled A through D, each with its own deadline and time to complete. Using this setup, we can demonstrate stable sorting, where sorting by a chosen criterion still preserves the original order among jobs that share the same key value. The script first announces that it is showing the original jobs order, meaning the sequence of jobs before any sorting is done. It then goes through each job in the list and prints its key details, such as the job name, deadline, and processing time. This output provides a clear view of the initial arrangement of jobs, which serves as a baseline for comparing how the order changes after sorting later in the program. We begin by sorting the list of jobs according to their processing time in minutes. To do this, we use Python's built-in stable sorting function, which keeps jobs with the same processing time in their original relative order. We set the sorting key to each job's time attribute so the jobs are arranged from shortest to longest processing time. This initial ordering prepares the data for any further sorting while preserving the order among jobs that take the same amount of time. Next, we sort the list of jobs a second time, now using each job's deadline, measured in days, as the key. Because the sorting method is stable, it keeps the relative order of any jobs that share the same deadline. That order was already determined by the previous sort based on processing time. As a result, the final list is ordered first by processing time, and then by deadline, while preserving the original order among jobs with equal deadlines. We first indicate that the jobs have been sorted by their deadlines, and when two jobs share the same deadline, they are further sorted by their processing time. Then we go through the sorted list and print each job's name, deadline, and processing time. This output lets us see the final order of the jobs and confirms that the stable sorting method keeps the relative order of jobs with equal deadlines by using processing time as a secondary sorting criterion. This script uses a job scheduling example to demonstrate how stable sorting works. It starts with a list of jobs, each having a name, a deadline, and a processing time. The jobs are first sorted by processing time in ascending order, and because the sort is stable, jobs with the same processing time keep their original order. The list is then sorted again by deadline, still in ascending order, and jobs with the same deadline keep the order established by the previous sort. The final result is a list of jobs ordered first by deadline and, when deadlines match, by processing time, showing how stable sorting preserves relative order across multiple passes. Greedy heaps and priority. Heap, push, and pop. In a greedy algorithm that uses a heap, you repeatedly push new candidate items into the heap and pop out the best available one according to a priority rule. The heap always keeps the most important candidate at the front, so each push adds a new option and each pop selects the current best choice to update your solution. For example, in task scheduling by deadline, you insert tasks with their deadlines as priorities and always remove the task with the earliest deadline first. This makes heap operations the central mechanism that drives the greedy decision-making process. When using heaps, write code that makes the priority of each item clear and easy to understand. Think about what each item represents and why it has its particular priority, such as a location with a cost in pathfinding or a project with an urgency score in resource allocation. The heap then simply returns the item with the most favorable priority, like the lowest cost or highest urgency. By choosing descriptive names and briefly documenting what priority means in your algorithm, you make the greedy logic behind your heap operations much easier to follow and maintain. In a greedy algorithm that uses a heap, it is important to control when you push and pop items, because this defines the structure of your strategy. You usually alternate between pushing new candidate options into the heap and popping the best one to move the solution forward until a stopping condition is reached. For example, in a support ticket system, new tickets are pushed based on priority, and the highest priority ticket is popped for action. You should be able to describe how the heap changes over time, where pushes add new options and pops select the next best choice. Making your explanation match the pattern in your code helps keep the greedy algorithm clear and maintainable. Python code: heap, push, and pop. We want to demonstrate how to use a heap to make greedy task scheduling decisions. By pushing tasks into a heap based on their deadlines, the task with the earliest deadline will always be at the top. When we pop from the heap, we always remove and process this earliest deadline task first. The example should use beginner-friendly code with clear comments and printed messages that explain each push and pop step and show why the earliest deadline tasks are always chosen before later ones. Here we are noting that we do not need to install any extra packages because the heapq module is already included in Python's standard library. This allows us to use it right away without additional setup. As a result, it becomes easier to manage priority queues, which we rely on for making scheduling decisions. We use Python's heapq module to implement an efficient priority queue based on a heap data structure. In this context, each task's priority is determined by its deadline. The heap lets us quickly insert new tasks and remove the most urgent one. As a result, tasks with the earliest deadlines are processed first, which helps us manage time-sensitive work effectively. We represent our tasks as a list of tuples, where each tuple contains a deadline in hours from now and the task's name. For example, we might include writing a project report due in 4 hours, replying to urgent emails due in 2 hours, and preparing meeting slides due in 6 hours. Organizing tasks this way makes it easy to compare their deadlines. This structure will later allow us to use a heap to automatically prioritize tasks by which ones are due soonest. We begin by creating an empty list that will act as our priority queue. Each entry in this list stores a deadline paired with a task name. By organizing the list as a heap, tasks with the earliest deadlines automatically move to the front. This structure lets us efficiently select and manage the most urgent tasks first. We process each task by taking its deadline and name, then insert it into a heap data structure. Using the heap ensures that the task with the earliest deadline is always positioned first. This organization lets us quickly find and select the most urgent task. As a result, it supports an efficient, greedy scheduling strategy based on task deadlines. The code prints the current contents of the heap to reveal how tasks are ordered inside the priority queue. By examining this output, you can see that tasks are arranged according to their deadlines. This ordering ensures that the task with the earliest deadline always appears at the front of the heap. In other words, the printout helps you visualize and confirm the internal structure and behavior of the priority queue. We simulate an urgent task by creating an entry with a very early deadline, such as 1 hour, and the description, "Fix critical server bug." This entry represents a task that requires immediate attention and has an earlier deadline than any existing tasks in the priority heap. By giving it the smallest deadline value, we ensure the scheduling system places it at the top of the heap. As a result, this urgent task will be handled before all other pending tasks. We add the new urgent task to the heap using the heapq push operation. This keeps the heap ordered, so the task with the earliest deadline always appears first. As a result, the scheduler can quickly see and select the most urgent task, supporting efficient, greedy scheduling decisions. We print the current state of the heap to see how adding a new urgent task changes its internal order. This lets us verify that the task with the earliest deadline moves to the front. In doing so, it clearly demonstrates that the heap structure automatically prioritizes tasks based on their deadlines. We use a loop that runs as long as there are tasks in the heap, so every task is eventually processed according to its urgency. In each iteration, we remove the task with the earliest deadline using the heap's pop operation, which is efficient because the heap always keeps the smallest deadline at the front. After selecting a task, we print which task was chosen and its deadline. This confirms that tasks are handled in the correct order, with the most urgent ones processed first. This script shows how a heap-based priority queue can be used to schedule tasks by their deadlines. It starts with a list of tasks, each with a deadline and a name, and pushes them into a heap so that the task with the earliest deadline is always selected first. After displaying the initial order, it adds a new urgent task with an even earlier deadline and shows how the heap automatically updates the priority. Finally, it repeatedly removes tasks from the heap, always taking the one with the nearest deadline, illustrating a greedy strategy where the most urgent tasks are processed before the others. Priority selection loops. In a greedy algorithm that uses a heap, the core idea is a repeated priority selection loop. At each step, you ask the heap for the highest priority item, remove it, and then perform whatever action the algorithm requires. Based on that action, you may update your state and insert new items into the heap if their priorities have changed. This cycle of selecting, acting, updating, and repeating continues until no more useful items remain. And a clear Python implementation should make this loop easy to see. Use a heap by first loading it with your initial candidates, each labeled with its priority. While the heap is not empty, repeatedly remove the top candidate according to your chosen rule, such as lowest cost or earliest time. After selecting a candidate, update your overall state, like marking tasks as completed or adjusting totals, and add any new or changed candidates back into the heap. Keep the loop easy to understand by using clear names, separating the selection step from the update step, and avoiding unrelated logic inside this core process. In problems like scheduling deliveries or managing support tickets, a priority selection loop repeatedly chooses the most important item that still fits the current constraints. For deliveries, this means picking the most profitable job that fits the route and time, then updating the route and adding any newly feasible deliveries to the priority structure. For support tickets, it means selecting the most urgent ticket, processing it, and adjusting related ticket priorities. The key idea is that the loop is not just about heap operations, but about clearly expressing the greedy rule that priorities drive each decision, so the code's logic is easy to follow. Python code. Priority selection loops. This example illustrates a greedy priority selection loop using a simple delivery scheduling problem. It relies on a priority queue implemented with a heap to always choose the next most profitable delivery that is still feasible. The process follows a clear pattern. Select the best available option, perform that action, update the state, and then repeat. This structure helps keep greedy algorithms both effective and easy to maintain. The code notes that you do not need to run any installation commands for the heapq module because it is part of Python's standard library. This means it is already included with Python and available by default. As a result, you can use it directly for priority queue operations in the script without installing any extra packages. We begin by importing the heapq library from Python's standard library, which lets us implement a priority queue using a heap data structure. In this context, priority is based on profit, so the heap makes it efficient to access the most profitable delivery at any moment. This capability supports the greedy strategy used in the rest of the script, where we repeatedly choose the best available delivery according to profit. We use a simple data structure called delivery, represented as a tuple, to store information about each delivery. This tuple contains 3 values: the start time, the end time, and the profit in dollars. Grouping these related pieces of data together in one tuple makes each delivery easy to handle as a single unit. It also simplifies how we manage and access delivery information throughout the rest of the code. We begin by creating a list of deliveries where each delivery is stored as a group of 3 values: its start time, its end time, and the profit in dollars. This list captures all available delivery options and their key details. By organizing deliveries this way, we can later sort and choose among them based on when they occur and how much profit they provide. The deliveries are sorted by their start times, so the system can quickly find which ones are possible to handle at the current moment. By keeping them in this order, the code can efficiently access only the deliveries that are ready to be processed. This makes the selection process both logical and efficient, since it focuses on feasible deliveries at the right time. We begin by setting the current time to 0 to mark the start of the delivery schedule and establish a clear reference point for when deliveries can begin. At the same time, we set the total profit to 0 so we can track how much money we earn as we go. As each delivery is completed, we add its profit to this running total, allowing us to monitor our overall earnings throughout the schedule. We start by setting the total profit to 0 so we have a clear starting point. This value will store the running total of profit from all the deliveries we choose. As we process each delivery, we add its profit to this total. Beginning at 0 simply gives us a baseline to accumulate these profits correctly. We create an empty list called the available heap to manage deliveries that are ready to be scheduled. This heap lets us quickly access the most profitable delivery at any moment. Because the default heap in Python always removes the smallest value first, we store each delivery's profit as a negative number. This makes the highest profit appear as the smallest value in the heap. With this setup, the greedy algorithm can efficiently choose the most profitable available delivery each time. The code starts by setting an index to 0, which is used to track which deliveries are currently available based on the time. As the loop runs, this index is updated to reflect newly available deliveries. This allows the program to consider only those deliveries that are feasible at the current moment. In this way, the scheduling process focuses on valid options and ignores deliveries that are not yet ready. The code first prints a header that explains the output of the greedy selection process. It labels the columns for the step number, the chosen delivery, the current time, and the total profit. This header makes it easier to follow how decisions are made and how the state of the algorithm changes at each iteration. We begin by setting a step counter to 1 to track the order of operations. Then we enter a loop that runs as long as there are unprocessed deliveries or available candidates in the heap. This combined condition lets us keep working through both new deliveries and those already waiting in the heap. The loop continues until every delivery has either been scheduled or identified as infeasible, ensuring that no possible option is left unprocessed. We repeatedly check whether any deliveries can start at the current time by looping through the list, while the index is valid and the delivery's start time is less than or equal to the current time. For each eligible delivery, we take its start time, end time, and profit, then push it onto a heap. We store the profit as a negative value so that the default min heap behaves like a max heap, keeping the most profitable delivery at the top. After adding a delivery to the heap, we move the index forward to examine the next one. The code checks whether there are no available deliveries in the heap, while there are still deliveries left in the list. When this happens, it moves the current time forward to the start time of the next delivery in the list. This time jump makes sure the loop can keep working by waiting until a new delivery becomes available. After updating the time, the continue statement skips the rest of the current loop iteration, so the loop can immediately recheck its conditions with the new time. We use the heapq tool to remove the most profitable delivery from the available options. The heap is organized using negative profit values so that the delivery with the largest profit is always selected first. When we pop from the heap, we get the chosen delivery and then separate its profit, end time, and start time into individual variables for later use. In this part of the code, we check whether the delivery's end time is already earlier than the current time. If it is, the delivery is no longer feasible because it cannot be finished within the allowed time window. In that case, we skip this delivery and continue to the next one in the loop. This way, the algorithm only considers deliveries that can still be completed, which helps maintain the efficiency of the greedy scheduling process. After choosing a delivery, we move the current time forward to the delivery's end time to show that it has been completed. We then update the total profit by adding the profit from this delivery. Because profits were stored as negative numbers to work correctly with a max heap, we add the opposite of that stored value, so the total profit increases by the correct positive amount. The code reports each decision made by the greedy algorithm by printing the current step number, the selected delivery's start and end times, and its profit. It also displays the updated current time and the new total profit after that delivery is accepted. This output gives a clear, step-by-step view of how the algorithm builds its solution. After printing this information, the step counter is increased to move on to the next iteration. The code ends by printing a summary of the total profit earned by the greedy delivery schedule. It uses a formatted string to insert both the final profit and the final time directly into the message. This creates a clear, concise conclusion that reports the outcome of the greedy algorithm. In one step, it communicates how much profit was made and when the schedule finished. This script illustrates a greedy algorithm for scheduling deliveries to maximize profit. It sorts deliveries by their start time and uses a priority queue to always pick the most profitable delivery that can be done next. As time moves forward, it adds all deliveries that have become feasible into the queue. And if none are available, it jumps ahead to the start time of the next delivery. At each step, it selects the highest profit option, updates the current time, and adds that profit to the total. The script reports each chosen delivery along with the updated time and running profit, and ends by summarizing the final total profit and the time when all scheduled deliveries are finished. Simulating priority queues. When you design a greedy algorithm that repeatedly picks the best available option, you are effectively using a priority queue, whether you name it that way or not. This abstract structure manages elements by their priority, often implemented with a heap in languages like Python. The key is to focus on the needed operations, such as adding candidates, updating them, and extracting the next best choice. By thinking in terms of a priority queue, instead of low-level heap details, your code will better reflect the algorithm's logic and be easier to explain and maintain. To simulate a priority queue, first decide what counts as priority in your algorithm, such as earliest deadline in scheduling or shortest distance in routing. Then, represent each item in the queue with a simple, consistent record that includes both its priority value and the information needed to process it. For example, you might store a task's deadline along with its identifier and duration, or a shipment's urgency with its destination and weight. Keeping this structure clear makes it easy to see which part determines the ordering in the queue and which parts are the data used by the algorithm. In a greedy algorithm that uses a priority queue, the queue drives all decisions. You begin by inserting all items that are immediately eligible, then repeatedly remove the best item, commit to that choice, and insert any new items that become eligible. This is similar to hospital triage, where you always treat the patient with the highest severity next, or network bandwidth allocation, where you serve the highest priority data flow and then update its priority. Organizing the algorithm this way keeps the code clear and adaptable because the logic is centered on simple priority queue operations. Python code, simulating priority queues. We can use the heapq tools in Python to simulate a priority queue in a simple greedy scenario, such as a triage system where patients arrive with different severity levels. Each patient is given a priority value that represents how urgent their case is, and the heap structure automatically ensures that the most severe cases are treated first. It is important to keep the idea of medical priority separate from the internal details of how the heap stores and orders the data. In practice, the standard library tools are enough for this kind of simulation, so no extra installation is required. We use Python's heapq module to treat a list as a binary heap, which lets us implement a priority queue efficiently. This module provides built-in functions to keep the heap structure correct when we add or remove elements. Because it is part of the standard library, we can use it without installing anything extra, making it a convenient choice for priority queue operations. This part of the code represents each patient as a simple Python tuple containing 3 pieces of information: the severity of the condition, the arrival order, and the patient's name. Severity is stored as a negative number, so it works correctly with the min-heap behavior of the heapq module, allowing more severe cases to be treated first. The arrival index is used to break ties when patients have the same severity, so earlier arrivals are prioritized. Together, this creates a priority queue where patients are treated based on both how serious their condition is and when they arrived. We begin by setting up an empty list that will act as our priority queue using a heap structure. Each item we store in this list represents a patient and includes their severity level, the order in which they arrived, and their name. By using a list with the heap tools, we can efficiently add new patients and always retrieve the one with the highest priority based on these values. We start by setting an arrival counter index to 0 to track the order in which patients come in. Each time a new patient is added, we increase this counter. This lets us record who arrived earlier. When 2 patients have the same severity level, we use this arrival order to decide who should be prioritized first, ensuring a consistent and fair ordering. This function updates a global arrival counter to track the order in which patients are added. For each patient, it creates a tuple containing the negative of their severity, the current arrival index, and their name. Using the negative severity allows a min-heap priority queue to treat higher severity as higher priority. The tuple is then pushed onto the priority queue, which maintains the correct ordering. Finally, the arrival index is incremented so each patient has a unique arrival order, which is used to break ties when severities are the same. This function first checks whether the priority queue is empty, and if so, it returns a message saying there are no patients waiting. If the queue is not empty, it removes the entry with the smallest stored value, which actually represents the patient with the highest severity because severities were saved as negative numbers. The removed entry includes the negated severity, the arrival order, and the patient's name. The function then converts the severity back to a positive number and returns a formatted message stating which patient is being treated and their severity level. We model a triage room by adding several patients to a priority queue. Alice is added first with a moderate severity level of 5, then Bob with a lower severity of 2, and finally Carlos with a high severity of 8, making him the top priority. A helper function adds each patient, so the queue automatically orders them by both how severe their condition is and when they arrived. This code prints the result of treating the next patient from a priority queue. It calls a function that uses a min-heap to select the patient with the highest severity. That function returns a formatted message stating which patient is being treated based on their severity level. The print statement then displays this message, showing the current step in the triage process. When a new patient named Diana arrives with a very high severity score of 10, we'll add her to the priority queue using a helper function that takes her name and severity. Inside this function, we build a tuple containing the negative of her severity, the current arrival index, and her name. We store the negative severity so that, even though the underlying heap is a min heap, patients with higher severity are treated as higher priority. This tuple is then pushed into the heap-based priority queue, and the arrival index is increased so the next patient will have a unique order of arrival. When a new patient named Evan arrives with a severity level of 4, we add him to the priority queue using the patient entry function, which takes his name and severity as inputs. Inside this function, we build a tuple containing the negative of his severity, the current arrival index, and his name. Using the negative severity lets the min heap treat higher severity values as higher priority. We then push this tuple into the heap-based priority queue and increase the arrival index so that future patients are kept in the correct order. We treat patients by always selecting the one with the highest priority from the queue. Each time the function is called, it removes and returns the patient with the greatest severity, represented internally as the smallest value due to using negative severity scores. This guarantees that the most urgent patient is treated first, then the next most severe, and so on. The process continues in this way until the queue is empty or all patients have been treated. The final call to this function handles the next patient in the priority queue. It first checks whether any patients are still waiting. If the queue is empty, it returns a message indicating that no patients remain. If there are patients, it removes and returns the one with the highest severity, based on the smallest tuple in the heap. This behavior ensures that patients with the most urgent needs are always treated first, following the rules of the priority queue. This example shows how to simulate a priority queue for medical triage using Python's heapq module. Each patient is added with a severity level, and because the heap is a min heap, severities are stored as negative values so that higher severity numbers are treated first. As patients arrive and are added to the queue, the system always selects and treats the patient with the highest severity next. When all patients have been treated and the queue is empty, the program reports that no one is waiting, demonstrating a dynamic and efficient way to manage priorities with a heap-based queue. Greedy performance analysis. Benchmarking greedy implementations. When benchmarking a greedy algorithm, the goal is to gather systematic evidence of how its performance changes as input sizes grow. Instead of relying on intuition, you run it on a range of realistic but manageable problem sizes, using datasets that reflect tasks like scheduling jobs or choosing marketing campaigns. For each input size, you measure runtime and memory use and repeat tests to reduce random variation. Analyzing this data shows whether the algorithm scales smoothly or if its performance breaks down on larger inputs. When benchmarking, you should carefully control and record the test conditions, using a stable setup on the same machine and minimizing other running tasks, while noting hardware and software versions. Be aware that initial runs can behave differently from later ones because of warm-up effects, such as caching, so early measurements may not reflect steady-state performance. To get a more reliable view of how something performs, repeat your experiments and summarize the results using averages rather than relying on a single measurement. After collecting benchmark data, You should analyze it to guide your design decisions. Plot runtime against input size to see whether performance grows roughly linearly, quadratically, or in a more complex way, and to detect any sharp slowdowns. For example, an algorithm might handle a few thousand deliveries well, but degrade beyond that, signaling the need for optimization or a different method. Finally, compare these results with real-world requirements such as acceptable user response times or batch processing limits to decide whether your greedy algorithm is adequate or needs further refinement. Python code, benchmarking, greedy implementations. In this activity, you benchmark a simple greedy algorithm for interval scheduling. As the input size grows, you generate random intervals, run the greedy scheduling implementation on them, and measure how long it takes to complete. By repeating this for increasing numbers of intervals, you can observe how the runtime changes with input size. To help visualize these results, you should install and use a plotting library such as matplotlib. We begin by importing the time library so we can measure how long our code takes to run. We also import the random library to generate random data for testing the algorithm. Finally, we bring in the statistics library to calculate average run times. Together, these tools let us evaluate the algorithm's performance across multiple runs in a clear and consistent way. We use the plotting tools from matplotlib to create visualizations in Python. Here, we use them to generate a line plot of the runtime of our greedy algorithm as the input size grows. Gisplot helps us see how the algorithm's performance changes with larger datasets and understand how well it scales. In greedy interval scheduling, we first sort all intervals by their finishing times, so we can always consider the earliest finishing ones first. We then keep an initially empty list of chosen intervals and track the end time of the last selected interval. Moving through the sorted intervals, we select an interval only if its start time is at or after the current end time, and then update the current end time to this interval's end. After checking all intervals, the selected list forms an optimal set of non-overlapping intervals according to the greedy strategy. To create random intervals for benchmarking, we use a function that takes the number of intervals we want and builds a list of them. For each interval, it picks a random start time between 0 and 10,000 and a random duration between 1 and 10. It then forms an interval as a pair of values, with the start time and the start time plus the duration as the end time. Each interval is added to the list, and when the loop finishes, the function returns the complete list of randomly generated intervals for use in benchmarking. This function measures how long the greedy interval scheduling algorithm takes to run for different input sizes. It keeps a list of average run times, and for each input size, it runs the algorithm many times on newly generated random intervals. For each run, it records the start and end times using a performance counter and stores the difference as the runtime. After completing all runs for a given size, it computes the mean of these runtimes using the statistics library and adds this value to the list. In the end, it returns the list of average runtimes for all tested input sizes. We define a set of input sizes, such as 1,000, 3,000, 5,000, 7,000, and 9,000 elements to represent different workloads for the greedy algorithm. Then, we run a benchmarking function on the greedy algorithm using these sizes. Each input size is tested 5 times, and the results are averaged. This repeated testing reduces random timing variation and gives a more stable measure of the algorithm's performance as the input size increases. We first print a header for a summary table that lists the number of intervals and their average runtime in seconds, creating a clear structure for the results. Then we loop through each pair of input size and average runtime. For every pair, we print the number of intervals and the corresponding average runtime formatted to 6 decimal places. This produces a concise, readable summary of how the algorithm's runtime changes as the input size increases. We create a plot to visualize how the greedy interval scheduling algorithm's runtime scales with input size. The horizontal axis shows the number of intervals scheduled, and the vertical axis shows the average runtime in seconds. Each data point is marked so we can see how runtime changes as the number of intervals increases. The plot includes a descriptive title and a grid to make the data easier to read. Overall, this visual representation helps us understand the performance behavior of the algorithm for different input sizes. This script measures how efficiently a greedy interval scheduling algorithm runs as the input size grows. It repeatedly generates random intervals, sorts them by their end times, and uses a greedy strategy to select non-overlapping intervals. For each input size, it runs the process multiple times and computes the average runtime. The script then prints a summary of input sizes and their average runtimes, and plots a line graph to show how the algorithm's performance scales with larger sets of intervals. This reveals the efficiency and scalability of the greedy approach for interval scheduling problems. Profiling greedy hotspots. After your greedy algorithm passes initial tests, you should profile it to see where it actually spends most of its time. Profiling reveals performance bottlenecks, which often occur in operations that run repeatedly, such as choosing the next best candidate or updating data structures. In something like a scheduling app, this might mean selecting the next job or updating machine availability. By profiling with realistic workloads, you can see whether the main cost comes from the selection logic, the data structure operations, or many small tasks like data conversion and logging that add up over many iterations. When you read profiling results, always relate the low-level numbers back to the structure of your greedy algorithm. If a function uses a lot of runtime, think about how it fits into the main loop and how often it is called. Small pieces of code can become major hotspots when they run once per element or per iteration. For instance, a comparison used in sorting or in a priority queue may be called millions of times. So, even tiny inefficiencies can dominate the total runtime. Profiling reveals these patterns and highlights which operations fail to scale as input sizes grow. Profiling helps you find where a greedy algorithm actually spends its time, so you can focus optimizations where they matter most. It may reveal that data structure updates or input parsing, rather than the heuristic itself, dominate the runtime, suggesting that improving these parts or separating pre-processing from the main loop will give better speedups. By repeatedly profiling after each change, You can confirm that your optimizations are effective and avoid unnecessary tweaks. This systematic process leads to greedy algorithms that handle large, complex inputs more efficiently. Python code, profiling, greedy hotspots. In this segment, we use a simple interval scheduling problem to demonstrate how to profile greedy algorithm hotspots. We compare a slow approach that selects intervals using a linear search with a faster approach that uses a heap-based selection, and we analyze both using a profiling tool. By running these methods on many random intervals, we can see which parts of the code consume the most time and become performance hotspots. This helps highlight how different selection strategies affect efficiency in greedy algorithms. The comment recommends installing optional tools such as a line profiler and a memory profiler to analyze Python code performance and memory usage. These tools help you find bottlenecks and understand how your program uses resources. They are not directly used in the script itself, but are suggested for deeper analysis than what the built-in profiler provides. We start by importing several Python modules that support our program. The random module lets us generate random numbers, which we will use to create random intervals. The time module can measure how long operations take, even though it is not directly used in this short example. We also import the profiling module cprofile to analyze which parts of the code take the most time to run. Finally, we use pstats to format and display these profiling results in a clear, readable way so we can spot performance bottlenecks. This function creates a list of random time intervals where each interval represents a job with a start and end time. It first sets up an empty list to hold the intervals, then repeats a process for the desired number of jobs. For each job, it randomly chooses a start time between 0 and a given maximum, then randomly chooses a length between 1 and a specified maximum. It adds the length to the start time to get the end time, stores the start and end as a pair, and appends this pair to the list. After generating all the intervals, the function returns the complete list of job intervals. This function is a slow, greedy scheduler that selects a set of non-overlapping intervals. It begins with an empty list of chosen intervals and a marker for the end of the last chosen interval. All intervals are sorted by their end times, and the function repeatedly scans the remaining ones to find the earliest finishing interval that starts at or after the current end time. If such an interval is found, it is added to the selected list, removed from the remaining set, and the current end time is updated. If no compatible interval exists, the process stops, and the function returns the list of selected intervals. The code uses Python's heapq module from the standard library to implement a priority queue based on a heap data structure. In this scheduling algorithm, the heap is used to quickly access the interval with the earliest end time. This makes the greedy strategy more efficient than scanning through all intervals each time. As a result, selecting the next interval is faster, especially when working with a large number of intervals. This function schedules intervals efficiently using a heap. It first pushes each interval into the heap as a pair of end time and start time so that intervals that finish earliest are processed first. It then repeatedly removes the interval with the smallest end time and checks whether its start time is at or after the end of the last chosen interval. If it is compatible, the interval is added to the list of selected intervals, and the current end time is updated. When the heap is empty, the function returns the selected intervals as an optimal schedule with no overlapping choices. The runSchedulers function is used to test and compare two versions of a greedy scheduling algorithm under realistic conditions. It first generates a large set of random time intervals, each representing a job with a start and end time. It then runs the slower, linear search-based scheduler on these intervals, followed by the faster, heap-based scheduler on the same data. Finally, it checks that both methods select the same number of intervals, ensuring they are functionally equivalent while allowing their performance to be compared. We use a profiler from the cProfile library to measure how long different parts of our code take to run. After enabling it, we execute the function that runs both versions of our greedy scheduling algorithms to generate realistic performance data. We then disable the profiler and create a statistics object from the pstats library to analyze the collected information. To make the results easier to read, we remove directory paths, sort the data by cumulative time, and print the top 8 functions. This reveals which parts of the code consume the most total execution time and are our main performance hotspots. This script profiles two greedy scheduling algorithms that select compatible time intervals from a set of randomly generated jobs. One algorithm uses a slow linear search to find the next interval, while the other uses a more efficient, heap-based method. Both are run on the same large set of intervals, and their performance is measured with the cProfile tool, focusing on cumulative time to find performance bottlenecks. The results show that the heap-based approach is much faster, illustrating how appropriate data structures like heaps can significantly improve the efficiency of greedy algorithms. Comparing to naive solutions. To understand the value of a greedy algorithm, it helps to compare it with a simple but inefficient naive solution. The naive version is not meant for real use, but it serves as a baseline to show how much faster the greedy method can be. For example, when scheduling jobs by earliest deadline, a naive approach might repeatedly scan the entire list or use brute force, while the greedy algorithm makes more direct choices. By timing both on the same inputs, you can see that the naive runtime grows quickly with input size, while the greedy algorithm remains efficient. This makes the efficiency benefits of smarter choices and appropriate Python tools clear and concrete. To compare greedy and naive algorithms, run experiments that show how their runtimes grow as input size increases. Start with small inputs where both are fast, then gradually increase the size until the naive method becomes too slow to be practical. For instance, in a resource allocation task, a greedy algorithm might use a heap to pick options efficiently, while a naive method repeatedly scans a list. As the dataset grows to thousands or millions of items, the naive approach slows dramatically, but the greedy one scales more smoothly. Observing this contrast reveals how algorithm choices affect performance in real applications like logistics planning or recommendation systems. When comparing a greedy algorithm to a naive one, focus on how their performance relates to the algorithm design and the size and type of data. If the greedy method only outperforms the naive one on very large datasets, it may be best suited for big data tasks rather than small interactive applications. If it is consistently faster, its added complexity can be justified by real benefits, such as quicker calculations or faster service decisions. Also pay attention to cases where the naive approach does unexpectedly well, since this can reveal weaknesses in your greedy solution or gaps in your test data. By studying these patterns, you gain a more practical understanding of performance than theory alone can provide. Python code, comparing to naive solutions. We want to clearly compare the performance of a greedy solution with a naive solution by measuring how long each one takes. Both approaches repeatedly select the smallest elements, but they do so in different ways that lead to different runtimes. The goal is to show this runtime difference in a simple, concrete way. We will use straightforward print statements that are easy for beginners to understand and run in a Google Colab environment. The key point is that no pip install commands are required because the code uses only Python's standard libraries. All needed features come built into Python, so there is nothing extra to download or configure. This is especially helpful in environments like Google Colab, where avoiding additional setup makes it faster and easier to start running the code. We begin by importing a time library so we can measure how long our code takes to run, which is essential for comparing the performance of different algorithms. We also import a random number library to generate test data for these algorithms. Using these standard tools lets us time and evaluate our functions accurately, without relying on any external software. To find the smallest k elements of a list using a simple method, we first copy the original list so it is not changed and create an empty list to store the results. Then, we repeat the following process k times. Assume the first element in the copied list is the smallest. Scan through the rest of the list to find any smaller value, and update the position of the smallest element when we find one. After each scan, we remove the smallest element from the copied list and append it to the result list. When this has been done k times, the result list contains the k smallest elements, which we then return by. We use the heapq module in Python to efficiently work with heaps, which are special binary tree structures that always keep the smallest element at the top. This is especially useful for building priority queues and quickly finding or removing the smallest values in a collection. By turning a list into a heap, we can repeatedly extract the smallest element in an efficient way. This behavior is exactly what we need for a greedy strategy that keeps selecting the smallest elements from a list. This function first makes a copy of the input list so the original is not changed, then turns that copy into a heap using the heapq library. A heap is a structure that lets the program access the smallest element very efficiently. The function then repeatedly removes the smallest element from the heap a specified number of times to build a result list. In the end, it returns this list, which contains the desired number of smallest elements from the original data. This part of the code defines a helper function that measures how long another function takes to run. It records the current time, calls the function we want to test with the given inputs, then records the time again after it finishes. By subtracting the start time from the end time, it computes the duration of the function's execution. This timing information lets us compare how efficiently different algorithms handle the same input. We use 3 input sizes, 1000, 5,000, and 10,000 to represent small, medium, and large datasets. These sizes let us compare how the runtime of our algorithms changes as the amount of data grows. By observing performance at these different scales, we get a clearer picture of each algorithm's efficiency. We set the value of k to 50 to specify that we want to select the 50 smallest elements from a list. This same value is used in both the naive selection method and the greedy selection method. Using the same k in both approaches ensures that they are compared fairly and consistently in terms of performance. We begin by printing a short header that explains the purpose of the timing table that follows. This header tells us we are comparing how long two different methods take to select a given number of the smallest values from a list. One method is a simple naive approach, and the other is a more efficient greedy approach. Stating this up front clarifies the context so we understand that the results show a performance comparison between these two strategies. We test performance by looping over different input sizes and, for each size, creating a list of random numbers between 0 and 1 million with that many elements. For each list, we time how long the naive method takes to find the smallest k elements. We then time how long the greedy method takes to do the same task. Finally, we report the list size and the measured times for both methods, rounded to 4 decimal places. So we can compare their performance across input sizes. This script compares two ways of selecting the smallest elements from a list. A simple method that repeatedly scans the entire list, and a greedy method that uses a heap for faster selection. It generates random lists of different sizes and measures how long each method takes to find a given number of smallest values. As the list size grows, the repeated scanning approach slows down dramatically, while the heap-based method remains much more efficient. The printed results clearly show that using a heap scales better and creates a growing performance gap in favor of the greedy approach. In this lecture, you learn to use Python sorting and heapq to implement efficient greedy selections, translate high-level greedy strategies into clear, maintainable Python code, and measure and interpret the performance of greedy implementations on realistic input sizes. In the next module, Module 8, we will go over dynamic programming. Thank you for your attention. See you all in the next lecture.